Hey guys, Jeff Foxworthy was right. I might be Sean May, and this might be a functional programming talk. I'm sorry. I hope lunch was great. Just before we get started, I want to say a huge thank you to my friend and colleague Fatima, who's an awesome designer who put that together. Now, just show of hands or a show of woos, who here came from Java and Spring, and who loves that ecosystem? Awesome. Okay, who loves C# and .NET and that world? Awesome. Who here is a gigantic functional programming nerd who loves JavaScript? Yeah, okay. So my goal is to not let that happen. My goal is, by the end of the talk, to have everybody have some common ground in terms of TypeScript and functional programming. Right? So this is going to get really nerdy. I apologize, but it will feel better in a bit. So once again, like Jeff Foxworthy said, that's me. I'm on Twitter at Sean J. May, and I am Norgard on Stack Overflow. I apologize if you have yelled at me in the past. This is the reason that I got into functional programming. I have seen too many code bases look like this in too many languages. How many people are with me? Awesome. So I found myself in positions where I was asked to fix code bases that I had, no hand in, but even just making the tiniest little change sort of felt like I was up against that. Right? When I'm looking at my IDE and that is staring back at me, I do not feel empowered to work with that code base. Right? So that brings me to thinking that really I need some strategy for working with code, for writing systems. I need something that's lightweight, adaptable, simple, and dependable. And it turns out that this talk is actually about Chun-Li. Right? Quick, agile, tactical, technical. Right? So because of that, and because of the Street Fighter tie-in, we're going to talk about a strategy guide, right? A strategy guide to functional programming in TypeScript. We're going to start with the basics, then we're going to move on to the combos, and then we're going to see some special moves, hopefully. All right, so let's start with the basics. Pure functions, right? I have a function that does nothing but take two numbers and return a number. Right? The concept of pure functions is that they don't modify anything outside of them. You can run that 1,000,000 times and you will always get the same answer. Right? If I make that a little more complex, you can see that it's a little more convoluted. I've got all of this type information in there. But all I'm doing is making some new vector to calculate distance, and then I am making and returning a new position based on that data, rather than just modifying the old position that I had. And the reasoning for that is actually pretty simple. Have you ever worked in a code base where the one on top doesn't work and the one on the bottom does? Has anybody not seen that? Right? So the answer is obvious, right? You just move C up and everything works. Come on. Right? So why pure functions? No races, no surprises. That is extra true for threading. Right? It's easy to debug, and you get this magical thing called referential transparency that will show up later. Don't worry about that for now. Right? So next on our list of basics, we have higher order functions. And higher order functions come in two flavors. The first flavor is a function that returns a function. And the second flavor is a function that accepts a function. Right? In JavaScript, we do that all the time in callbacks. Again, we'll see that in a bit. So the first kind, a function that returns a function. Remember x, right? I pass in a number, I get a function back. That function that returns the x. Right? So I'm saving out x6, x10, x23 for the nerdy in the room. Those are weapon x members. So I can call each one of those functions and it will return the remembered number. Right? Now, if the arrow functions are a little odd to you, we can do this in the ES5 way. Right? So the ES5 way, the necessary typing, which is enough typing for TypeScript to know what's going on. We have remember x, which takes a number and returns a function which returns x. Right? The extra typing, the very explicit typing, right? We have a function remember x, which takes a number, which returns a type function number, which returns a function of type number, which returns number. Right? That might be a little overkill, but if you think that's overkill, the explicit typing for the ES6 version is this. Right? So being explicit is not always a great thing. Right? This is way more information than TypeScript needs to do its job. In fact, the information that TypeScript needs to do its job is that. Right? That's going to do all of your type checking for you. If you have IntelliSense, it's going to tell you what the type is of the returned function or the number. It is smart enough to do that so that we don't have to care. Right? So, again, moving a little forward, we see clamp. We have a min and a max, which returns a function x. This lets me make multiple clamps and clamp to multiple values, right? I can clamp x and I can clamp y, and those are just reusable functions now. I can use them all over my system, right? So I can make a new point based on clamp x and y based on my current position. This gets into the second form and starts blending the two. I'm passing in a test now. So once I pass in a test, I get back a function that expects an A and B, and I test that one way, I test it the other way, and I'm going to return 1, -1, or 0 based on how things go, right? You've seen that in sorts all over the place. But what's really handy here is I can make these ascending and descending sorts, save them in my system, and reuse them all over the place. Right? That is the benefit of this type of higher order function. So I know what you're thinking. That looks like a whole lot of any, doesn't it? And you're right, that might lead to a whole lot of any's. I have you covered. Right? We're not going to spend a whole lot of time here, but if you look, I've got types for a comparator, comparison, and compare, and really, one is a typed function using generics, the other is a typed function using generics, and again, I have the third one, which is another generic function, which returns a comparison after you hand it a comparator, and that will remember all of the types, right? So the code below, again, those types shouldn't be there with the code, but the code below can look that clean and be type safe. Why? Right? It is reusable, it's configurable. I'm separating what I'm doing from how I'm doing it, and I can combine these. Map and filter are other very, very basics. They're primitives, right? So to uppercase on a string, just call string to uppercase, right? So I can map over that array and call to uppercase on it, and I get ABC back. Again, I can do the same thing with filter and pass it a predicate rather than a transform, and it's going to return me the right thing. And you replayed that slide. That's okay. Go me. Okay, so again, this doesn't have to be just functions in and of itself. I have a point here with a static from method. And that's going to take some coordinate, and it's going to return a point. Right? So I can use map and just pass in point from and get a list of points out of a list of coordinates. I don't actually have to run that function and do all of those things. That from, which is called an isomorphism, again, really nerdy, don't worry about that, will take care of that for you. Pick up items, right? I can map items and I can filter where each item is in range based on where it is and where I am, right? And all of the picked up items from that tick are going to be based on that filter predicate passing. Why? Again, I'm separating the logic from the flow. I get to define these tiny little functions which do one job and do that really, really well, and then just control how that flows through my system. It's a very simple pattern to pick up, and the paradigm of map and filter apply to way more than arrays. We'll get there, and they're very easy to chain. Speaking of chaining, that leads us to combos. Right? So you want to combine functions as a pipeline for data. We have this updated player which is going to take some player, and it's going to run it through update player position, then it's going to run it through update player animation. And at the end of that, I have this new updated player. Right? Again, we might do that for threading purposes, we might do it for concurrency purposes, we might just do it for memory safety and module management, and it doesn't really matter. So, I have this updated player, or I could just run that updated player through update player animation, passing in a repositioned player that I already got from somewhere else, right? Or that function could do double duty and I pass in player. This is actually the magic of referential transparency that I was talking about before. And referential transparency basically means that it doesn't matter which one of these I use, because the return value of a function is the same as having a value that is equal to the transformation of that function. I can replace a function call with a value that is represented by its return. Right? So compose lets me simplify this. I can take two functions, g and f, and return a function that expects x. And as soon as I run that over x, whatever x is, I will run f over x, and then I will run g over the return of f of x. Again, that's the referential transparency talking. It wouldn't matter whether it was f of x or it was just some fx transformed value. Right, so I can add one and double, and you can see I have this compose function where I am passing two functions. X returns x plus 1, and x returns x times 2. And they're written upside down because math. If you look at the body of the compose function, you'll actually see why it turns out upside down once you start adding new lines. So an add 1 on double on 3 is going to be 8. And again, to combat the people who are like, what about the any type? I have a transform type that takes some function with a generic A and returns a generic B, right? And compose just takes 3 generic arguments, A, B, C, and it takes the first transform from A to B, it takes the second transform from B to C, and it returns a new function that is a transform from A to C, right? So it's hiding what's going on under the covers. It's saying, give me the functions, I will return a function that takes your input value and returns your output value. And again, TypeScript is going to hold on to all of that. So the compose of this particular type, again, totally type safe despite the fact that you can't actually see any of the types defined in there. TypeScript will figure those out. The one type that I'm adding is actually the type of the input value for the first function, x equals number. As long as I pass that in, TypeScript is smart enough to be able to follow the chain all the way back up and figure out what you're getting at the tail end. Right, so again, in a slightly larger example, player update is just a transform from player to some new player, right? And I have update position, update animation, update health, and update all is going to be a compose of update health and also the composition of update animation and update position. Right? So I can compose composed functions. And this is where functional programming sort of gets a little magical, but as long as you remember that I'm returning new values, I'm not doing anything magical with private state. It's just input and output. Then I can compose these all day long, and TypeScript will be totally happy with it, and so will your code base, hopefully. Right? So again, a different type of chaining, a different type of combo is chaining map and filter calls in a pipeline. Right? So Injured enemies. If I want to deal damage, all I need to do is filter for all of the enemies that are in range of some attack range, some attack radius, and map deal damage over them with that damage value, right? And what comes back is a list of enemies that have taken damage this round. And it will only be those enemies, right? So again, updated players, I can map over a list of all players and pass in that update all function that we just wrote. Now, really important to note, mapping is not about loops at all. Mapping is actually about going from type A to type B. And this is key, right? So if I've got that transform again, and I have some map to point, which takes a coordinate and returns a point, and I'm just calling point from, which we saw earlier, I can call that on a new coordinate and get a new point. That's a map, right? I can take an array of coordinates and map to point over them, and I get an array of points. I can take a promise and then it over map to point and get a promise of a point back. I can take some stream, observable stream, and map to point over it and get an observable of points back. Right? TypeScript, again, will remember all of those types and keep you safe. Well, that was interesting. Now, the why? It becomes really easy to reason about with practice. You can build pretty big systems with this technique. Right? Dataflow is predictable. If you have separated your functions and your transformations from how you're composing systems, then your system just has to worry about what is my input and what is my output. Uncle Bob would actually be a very big fan of that. It's easy to add or change links in the chain. So if somebody comes along and says, you also need to filter for this case, you add a filter in the middle of that pipeline and you're done, right? And you can logic about where that filter fits. It's easy to compose functions in a chain. And if each link is pure function, then the whole chain is pure. And that's great news, because then you can use that whole chain as the input to some other composition. And it's testable, right? You can test the logic of an individual function, and you can test the chain as a whole. Okay, so the last piece, special moves. We have read-only, we have pick, and we have record. And we'll spend a little time on each. So read-only is actually a really, really handy type. It's basically an interface which will take in whatever generic you pass it, and it will then tell the compiler to expect that all of the members of that type are read-only. Right? So if you wanted to make read-only immutable classes in TypeScript, you usually have to declare a member read-only, like a read-only private or a read-only public. Now you can just say, it's a read-only account. Right? So if I get account by ID and it returns me a read-only account, if I try to manage that, if I try to change the value, it's going to throw an error at compile time in my editor. If I have some tamper-proof function which takes a read-only and returns a read-only, then I can handle transactions with wallets with the expectation that my code is not allowed to mutate the state of any wallet. That is a pretty big deal. Right? Caveat implementor. It doesn't save you from mutating private state in method calls. So do this with structs and not with Java-esque classes. All right, so here we have a pick. And this is a little harder to see because it requires a little bit of setup, but the point of pick is to pick a subset of an object with the types intact. So if you were just copying key value pairs onto some new object to get a subset, TypeScript is usually going to say that object is any, right? I have no way of guaranteeing that those types aren't going to change. But here, I'm saying I've got some band member and I'm going to pick the keys of person out of them. So as long as all of the keys of person are within band member, TypeScript is going to remember the types off band member. If those two types diverge, TypeScript is going to complain. If you have a key in person that is not in band member, TypeScript is going to complain. Right. That's funny. Just before that, that's where that missing slide went. Okay. So with record, the point is you can specify types of keys dynamically. You can build a record to say, my fields are going to be A or B or C or D. And all of them are going to be of type number or type string or type person. So with that in mind, thank you very much.